The Euclidean algorithm is one of the oldest and most efficient methods for computing the greatest common divisor (GCD) of two integers. The GCD of two numbers is the largest number that divides both of them without leaving a remainder. Before introducing the Euclidean algorithm, let's explore a more basic approach, prime factorization. Let's try to find the GCD of numbers 48 and 18. The number 48 can be expressed as the product of 2 times 2 times 2 times 2 times 3, which is the same as 2 to the 4th power times 3 to the 1st power. Similarly, the number 18 can be expressed as the product of 2 times 3 times 3, which is the same as 2 to the 1st power times 3 to the 2nd power. The prime factors they have in common are 2 to the 1st power and 3 to the 1st power, which, when multiplied, give the GCD of 6. Another approach using the same principle is to list all the factors of 48 and 18, identify the common ones, and select the largest, which is the GCD. First, check if the number 2 is a factor. It is, because it divides 48 into 24 parts with no remainder. The number 3 is also a factor because it divides 48 into 16 parts with no remainder. The number 4 is a factor because it divides 48 into 12 parts with no remainder. The number 5 is not a factor of 48 because it leaves a remainder of 3 when dividing. Finally, the number 6 is also a factor of 48 because it divides 48 into 8 parts with no remainder. There is no need to check the number 7 because we have already checked all numbers from 2 to 6. The smallest number that 7 can be multiplied by, which hasn't already been checked, is itself. However, 7 times 7 is equal to 49, which is greater than our original number, 48. This is why checks are only performed up to the square root of a number to avoid unnecessary calculations and improve the efficiency of the algorithm. Let's collect the factors of 48 and arrange them in a list. Now repeat the procedure for 18. First, check if the number 2 is a factor. It is, because it divides 18 into 9 parts with no remainder. The number 3 is also a factor because it divides 18 into 6 parts with no remainder. The number 4 is not a factor of 18 because it leaves a remainder of 2 when dividing. Let's collect factors of 18 and arrange them in a list. Identify the common factors between these two numbers and pick the highest, which in this case is 6. And that's how you find the GCD of 48 and 18 using this method. Now, let's explore the method of finding the GCD of two numbers using the Euclidean algorithm. At each step of the algorithm, the greater number is divided by the smaller number, and the quotient and remainder are recorded. So, 48 is equal to 2 times 18 plus 12. Now we replace the numbers 48 and 18 with 18 and 12 and apply the same process. Divide 18 by 12. The quotient is 1, and the remainder is 6. 18 is equal to 1 times 12 plus 6. Since the remainder is not 0, we continue with the next step using 12 and 6. The number 6 divides 12 exactly with no remainder. In other words, we express this as 12 is equal to 2 times 6 plus 0. Since the remainder is 0, the algorithm stops here, and the greatest common divisor of 48 and 18 is 6. You can see that this method required only 3 steps to find the GCD of 48 and 18. By working backward, we can express 48 and 18 in terms of the GCD. First, we rewrite 48 as 48 is equal to 2 times 18 plus 12. Next, each instance of 18 is replaced using 18 is equal to 1 times 12 plus 6. Finally, each instance of 12 is replaced using 12 is equal to 2 times 6. This shows how 48 and 18 can be fully expressed in terms of the GCD value. The reason why the Euclidean algorithm works is that the GCD remains the same at each step of the algorithm. The GCD of 48 and 18 is the same as the GCD of 18 and 12, which is the same as the GCD of 12 and 6. Since 12 is a multiple of 6, the GCD of 12 and 6 is 6, making it the GCD of all preceding pairs in the algorithm. We explored 2 methods for finding the GCD of two numbers, trial division and the Euclidean algorithm. Computationally, These methods require a different number of steps to complete. Trial division, on average, runs in O of square root of n steps, whereas the Euclidean algorithm finds the GCD in O of log of n steps, making it significantly faster. To truly appreciate the difference in performance between these two algorithms, let's choose a large value for n, such as 100 million. In this case, the approximate number of steps required for trial division is 10,000, while the Euclidean algorithm requires only about 27 steps. Now you know that when you run the GCD method in a library of your favorite programming language, it uses some variation of the oldest known algorithm under the hood, the Euclidean algorithm.